Okay, so this is a talk about peer prediction, which we can think about as a problem that I think is unusual because it's both very fascinating to study, but it's also, I hope I'll convince you of, practically important and interesting. So information elicitation without verification. Let me give you some examples. I could be encouraging people to deploy sensors to participate in a sensing system. So think about a sensing system around a city. Why without verification? I don't want to assume that I have access to any ground truth information about the information local to the sensors in the city. I could be looking to collect emotional responses to video content. This is something you could imagine would be useful for marketing, for kind of improving what Hollywood is doing. I could be looking to complete a consumer survey, asking you what features of a digital camera would you find interesting. I could be crowdsourcing feedback on my search algorithms. Is my tweak I've made to my product search algorithm worse or better than the last version of the algorithm? I could be peer grading in MOOCs. So in all of these settings, I think either you'll agree with me that it's true that there's no access to some verifiable ground truth. There's kind of there's nowhere to ground the information that's reported to the system. Or at least you would agree that it's costly to get that information. So we're in a setting where I'm also further going to assume that if I ask users, in the sensing example, I'm asking you to keep your sensing device well maintained, so that's costly. In the emotional response to content, I'm asking you to tell me whether you found the scene I've just shown you exciting or kind of nervous-making or other things. In the consumer survey, I'm asking you to really introspect about what's important to you. So I think in these settings, we can imagine that it's costly for you to invest effort in this task. So I'll need to somehow reward informative responses. And the thing that I'm going to worry about is that the reward scheme that I design might unintentionally introduce additional bad equilibria. So I'm going to have to pay for information. And now I want to pay for information in a way where by doing that, I don't unintendedly introduce new things that are happening where I'm getting, let's say, bad information because the participants maximize their payments by providing bad information. I'm going to worry about collusion as well. Okay, so how can we do this? How can we solve this problem of information elicitation without verification? There are two kinds of mechanisms in the literature. This is a problem that's been studied for quite a long time. One class of mechanisms are minimal, meaning that I'm only going to ask agents for information. We'll call that their signal. So I'm only going to collect signal information. Second class of mechanisms, we'll just call them non-minimal, ask for signal information and for the belief that you have about the signal that another agent in the system will receive. So say we're grading assignments, you think the grade is a B. What is your distribution you now place on the grade that will be assigned by another random person in the population? I'm interested in practical information elicitation without verification. So I'm just going to talk about minimal mechanisms in this talk. So mechanisms that only ask for information, not beliefs. Okay, so the simplest scheme for this, which is called simple output agreement, and if you've ever heard or played the ESP game, you've seen this. Let me also set up the model just a little bit, but we'll get back to this in some detail. I want you to think about two agents. These agents you can think about as being randomly sampled from some large population. And I want you to think about a joint distribution on the signals of those agents. Okay, so here the joint signal distribution here is P. The random variable is X, are the signals that agents will get. The realized values of the signals, I or J, will typically denote I for the realized value of the signal for agent 1 and J for agent 2. We're interested in settings where the signals are discrete and are non-binary. So there are more than just yes or no answers. And the simplest scheme you might think about is design a game where I take reports. So Costas makes a report and Eric makes a report. In the binary setting, the reports are 1 or 2. And if you agree, I pay you 1. If you don't agree, I don't pay you. Okay? This is a simple output agreement mechanism. Let's say that one of the things we're interested in is strictly proper mechanisms, where truthful reporting is a Bayes-Nash equilibrium. So when is this mechanism strictly proper? When is truthful reporting a Bayes-Nash equilibrium? Well, what you have to think about is when you get signal 1, conditioned on you having signal 1, what is your belief that the other agent will get signal 1 or signal 2? And so if the conditional probability of the other agent getting 1 conditioned on you getting 1 is greater than conditional probability of the other agent getting 2 conditioned on you getting 1, you'll happily report 1 in that case. That will maximize your expected payment. So that's the condition that's needed in this setting. Let me see if I can kill that. For strict properness.
Instead of preview, see if you could use Adobe. I think that might be the problem.
No. Let's see. Does that not?
Because you're in the Apple preview instead of the Adobe land.
That's better, I think. Okay, so this is a condition that we need. You know, this is not always going to hold. So that's one problem with this scheme. You can think about it if it's very unlikely, generally, that the signal in the joint distribution is 1, then even conditioned on you getting a 1, you may place more weight on the other agent receiving signal 2. So that's one problem. But a bigger problem, and the problem that I'm going to focus on in this talk, is yes, there is a strict Bayes-Nash equilibrium here when this condition holds as truthful. But there is an uninformative equilibrium where we both say 1 all the time. It's a Nash equilibrium. That has higher expected payment. You get 1 all the time. So that's a problem. That's one reason why you might not actually like to use this scheme in practice. I pay $1 every time. I don't get any information. The signals reported are not correlated in any way with the true signals. Okay, so this problem was solved. This was solved, and this was the paper that introduced the peer prediction method. This was solved by saying, okay, I'm going to do the following. I'm going to receive report R1 from agent 1. I, as the mechanism, will form the conditional belief that agent 1 should have about the signal of the other agent. And I will use this belief in a proper scoring rule. And I will score you as agent 1 using that belief against the reported signal of the other agent. Okay? If you think about it, if you've seen proper scoring rules before, and you think about it, and if you also assume that the model of the mechanism is correct, that is, it's correctly updating and forming a belief on your behalf based on your report, this is going to strictly align incentives in equilibrium. So what did this do? This is now strictly proper. I don't need to say strictly proper if X, Y, Z is true. It's strictly proper. But now the designer needs the model. Well, that's hard to motivate in practice. And we still have this problem of uninformative equilibria. In fact, if you write down the payoff matrix corresponding to this method, you're now going to see that whereas the old payoff matrix was 1s and 0s, there are multiple numbers in this payoff matrix, and you will coordinate on the one with the highest value. Okay, and that will be a Nash equilibrium. So we haven't solved that problem. This is a scheme that relaxes the knowledge requirement. So there are various schemes that do that. This is a scheme that looks like output agreement, but rather than paying $1, pays $1 divided by the signal prior. In other words, if we both agree on something that is ex ante unlikely, we'll get paid more. I refer to this as the 1 over prior mechanism. I'm not going to show you the math behind this, but suffice to say that this is strictly proper, always, for binary signals. For more than 2 signals, you need some technical conditions. it looks a little bit better than the MRZ mechanism, the one I described on the last slide, because the designer doesn't need as much information. The designer only needs the marginal probabilities now. But it still has this problem. It still has these bad uninformative equilibria. It's very clear here, I think. You're going to coordinate on the play where the marginal probability was the smallest and get paid a lot of money.
So what type of, is the underlying distribution symmetric with respect to the two guys, the two agents?
Let's assume it is here. So I'm assuming in all of these examples that the payment is the same to both players. If it's not symmetric, you can write down two numbers rather than one number. Okay. So I hope that this opening narrative leads to a set of desiderata that we'd like for real-world peer prediction mechanisms. We'd like them to be minimal, so we only ask for signal information. We'd like them to be proper. Perhaps we'd care about strictly proper, meaning that there's a strict equilibrium to be truthful. We'd like low knowledge requirements on the designer. And these kind of issues about coordination on uninformative high payment equilibria suggest there are other properties we care about as well. And this talk is going to be about achieving these additional properties. So the other properties we might care about is strong truthfulness, which will say that being truthful, playing the truthful strategy profile, has at least as much expected payment as anything else that could be done. And if there's a tie, then you must be playing a permutation strategy. So you must be playing 1 maps to 2, 2 maps to 3, 3 maps to 1. Okay? So strong truthfulness is essentially going to say that truthfulness gives you strictly more payment than any other pair of strategies the players could adopt. I'm not saying any other pair of strategies in equilibrium, just any other pair of strategies. That's a strong property. Informed truthfulness is a slightly weakened form of that. It's still going to insist that being truthful provides the same expected payment, at least as much expected payment, as any other joint play. And now it's also going to insist that if you play an uninformative strategy, you have strictly less expected payment. So what's an uninformative strategy? It's a strategy where your strategy doesn't depend in any way on the signal in the world that you've received. So in other words, this uninformative property, this informed truthfulness property, takes the design stance that the thing we're really trying to achieve here is to get players to invest effort in acquiring a signal, and that if conditioned on having invested effort to acquire a signal, they have the same expected payment for both being truthful as other things they could do, then they'll choose to be truthful, because truthfulness will somehow be focal amongst the class of informed play. So that's this informed truthfulness property. Yeah, Nicole.
I'm a little confused about the definition in terms of deviations being unilateral versus pairwise deviations. So are you saying that my truthful report with any report of the other guy should be better for me than any pair of things that we otherwise could do? Or
yes, I'm going to provide some formal definitions, but yes, that's roughly what I'm saying. And we'd also like to handle heterogeneity. So we'd also like agents to somehow differ in the way they respond to the world. So that goes to Costas's question. We're going to be willing to assume that there are multiple tasks. There are multiple independently sampled tasks that agents are performing. Right? It's like you're grading more than one assignment. So what do we know about this? Here's what I think we know about this problem. Jurka Faltings had a paper where they said that if there are at least 4 agents, even just with one task, not multiple tasks, in the binary setting, they can knock out these pure uninformative equilibrium. However, they ignore mixed equilibrium, and they're only in the binary setting, and the design needs access to the model of the world. There's a paper by Dasgupta and Ghosh, 2013, which will provide the background to the technical work that we do in this paper. They're in a multiple tasks environment. They achieve the properties that I say are important. They achieve strict properness and strong truthfulness, but they're only in the binary truthful setting. They're only in the binary signal setting. They're only yes/no answers. There's a paper by Radonovich and Faltings. It's also in the multiple task setting. They now do extend to multi-signal, and they get strict properness and strong truthfulness amongst symmetric strategies. Again, we'll get to the formal definition of that. But the catch here is that they only achieve this for asymptotically large numbers of tasks. There's a paper by Campbell et al., including Nihar Shah, who's over there in the audience. Very similar setting, actually. Their results do depart a little bit from the Radonovich and Falting setting. Again, multiple tasks. They achieve strict properness and strong truthfulness among symmetric strategies. They handle multi-signal, but again, they're working technically in this asymptotic environment. And for multiple signals, they need homogeneous agents. And then the final paper I'll mention on the theory slide, also by some people in this room, including Costas and Yang and Christos. It's a different setting, but I wanted to mention it. Again, I've pulled it into the setting of my talk. Multiple tasks. The tasks have kind of a distinct but known context. What's interesting and different about their model is they allow for non-binary effort. All of these other papers are implicitly thinking about a binary effort context. You either try to get the signal or you don't try. They're doing something more sophisticated than that. They get optimal efforts in a unique and dominant strategy equilibrium. But the catch relative to the work that I'm presenting here and these other papers is that they're ignoring the possibility of misreports. And so in the sense of the definitions in this talk, they don't get either strong truthfulness or is the scheme proper. So it's all about effort. And finally, I'll mention Alice's paper at the back here. So there's a very nice experimental paper by Alice and Andrew and Yiling and Ryan that says this all matters. They ran an experiment on Amazon Mechanical Turk, and they showed that either somehow participants seem to go to the uninformative equilibrium, or they just seem confused. Okay, so this all seems to matter. We don't really seem to know how to design these things. What do we do? Okay, so what do we do in this paper? How long do I have, Eric?
Until like 12:15.
12:15. Okay. So what do we do in this paper? So first of all, we study what we call the output agreement mechanism. It really takes the output agreement idea, the simple output agreement scoring mechanism, and takes it to this multi-signal and uses it in the context of a multi-task setting. This result will achieve strict, proper, and strong truthful for a multi-signal setting, but it will require domains to be categorical, and I'll explain what I mean by that. This result generalizes the Dasgupta-Ghosh results from binary signal to multi-signal. If you now allow me to use a little bit of domain knowledge, so I'm not going to assume access to the full joint distribution. Conceptually, I'm going to assume that I know the structure of correlation in the world. Then I can do more than this. We have what I'll describe as the 0-1 mechanism, which provides informed truthfulness and properness for general multi-signal domains and also handles heterogeneity. Okay, so it's giving you informed truthful, not strong truthful. But I hope I managed to convince you that informed truthful itself seems an interesting concept. And then we have what we'll call the ABCD mechanism. Hopefully you'll see why. It's not a very imaginative name, which provides strong truthfulness amongst symmetric strategies, again, for general multi-signal domains with heterogeneous agent types. The curious thing about this design is it's not proper. So it's strong truthful amongst symmetric strategies, but not proper. However, we can also show that meaning that truthful reporting is not an equilibrium. But we can also show that all equilibrium are strictly worse than truthful play in a large system. So if you're following me, that's kind of like a prisoner's dilemma. It's like if we somehow coordinate, then we get more payoff than if we deviate and play the equilibrium. So I don't know what to say at this point about whether this is practical or not. Seems like it's an interesting empirical question. And we've also done some empirical analysis. So we have access to around 100 questions across 30 exercises and around 17 MOOCs, and altogether around 325,000 peer evaluation responses. I'm going to show you a little bit about that as well. Okay, so now to get to the model. So the basic setup is going to have two agents, 1 and 2. You can think about them as being drawn from a larger population. There'll be tasks K. There'll be at least 3 tasks. The signals I and J are on the domain 1 through M, and it takes effort to acquire a signal. We have a joint distribution. We don't need that to be common knowledge. We also don't need that to be known by the designer. But we might need some of the structural properties of that to be known by the designer, and it may be asymmetric. Crucially, there are going to be some tasks that will be overlapping and some tasks that won't be overlapping. So if you just think about 3 tasks and 2 agents. So these are the tasks. Imagine that agent 1 is given these tasks and agent 2 is given these tasks. Then this is my shared task. This is my task that goes to agent 1 only, and this is my task that goes to agent 2. Okay, so what is multitask peer prediction? What we're going to do is for every shared task, we're going to compute a payment. It will be the same payment to both agents, and it will use the reports on that shared task. These are the reports on the shared tasks. And it will use all of the reports that agent 1 made on its own exclusive tasks, and all of the reports that agent 2 made on its own exclusive tasks. Okay? And that will compute a payment on a shared task, and will add up the payments across all of the shared tasks. So the scheme will decompose over shared tasks. What is a strategy? A strategy might be randomized. So a strategy for agent 1 is denoted F, for agent 2 is denoted J. And F sub IR is the probability assigned to report R if your signal is I. And G sub JR is the probability assigned to report R if your signal is J. We can show that it's without loss to assume task symmetric strategies. So we're not going to need these strategies to vary by the task. I'm going to skip the technical reason for why that's the case. And we have these 2 notions that you should understand to be able to follow the statement of the results. The first one is, what does it mean to have an informed strategy? This just means that your conditional distribution should change for some pair of signals, I and J, and then a truthful strategy will denote by asterisk. Okay. Are there any questions about the setup of the problem? Yeah, Vince.
So do the agents know which is the shared task?
We're going to assume the agents do not know which are the shared tasks. So you can think about doing that by randomization after the fact, for example.
So I don't understand the notion of tasks.
Tasks. So think about a task as, here's an image, is it a cat or a dog?
And what is the signal? How is the signal related to the task?
And so I'm just going to talk about joint distributions on signals, but if you want to make it more concrete, the image could have a kind of a latent type, which in this case I'd say is either it's a cat or a dog, and then you, in a conditionally independent way, and a noisy way, if it's a cat, you have some probability you'll say cat, and some probability you'll say dog. So if you want to make it concrete, I can have images. I can have my images be associated with a background distribution on the latent type of the image, and then you're a sensor and you get a noisy sample of that type. But I'm not going to go into the latent model. I'm just going to talk about joint signal distributions.
So in the agent's mind, or is there a joint, like everybody has a common distribution that relates signals to, correct labels for these tasks? Or?
Right. So the technical results will be stated as Bayes-Nash equilibria. However, a word that Nihal used, they're detail-free. So there'll be specificity of the distribution that won't matter to you playing in a particular way. So I don't need common knowledge, but I need some structural properties to be understood. Yep.
David, you mentioned effort earlier.
Right.
I would have thought that effort would affect the probability that I get an accurate signal.
Yeah, so that's what I was saying about the binary effort model. This is actually on my future work slide, and there are papers like Costas' paper and other papers. So, for example, work by Arpita Ghosh, and I think Preston may have been involved in those papers as well, with more sophisticated models of effort and also the kind of the contest literature as well. This literature, oftentimes actually if you read these papers, you won't see any mention of effort, but I think it's very helpful to think about it as a binary effort model. You either know nothing, and therefore all you can do is play an uninformed strategy, or you invest some cost and you get a signal. You can't control how noisy that is. You get a signal, and then you condition your play on that signal.
Well, I guess the main thing is that you could have a continuous effort, but it determines the probability that you get the signal. But if you do get it, the signal is exactly like that. It doesn't depend.
Yeah, I mean, you can imagine multiple ways to model what it means to have a non-binary effort model, but I don't have anything to say about that here. I haven't thought about whether the results will generalize or not. Yeah, James.
Do you model the cost of the binary efforts?
We don't need to model it because once we can show that, let's say there's a separation between being truthful and anything else, I can always scale the payments. Now, I'm not telling you how to scale them, but in principle, that's the idea.
So the final utility is the payment.
Right, good. So the only thing the agents care about is money. They don't care about anything, any decision that's being made based on the reports.
Not even cost.
They do care about cost, but I'm not modeling that cost explicitly. But I'd like you to assume that the expected payment for being truthful is greater than your cost. Okay?
What is F star?
Truthful strategy. So in a subjective perspective. So Costas looks at the image, he says, I see a cat. So truthful would mean you say cat.
I don't say cat. I get something like I get a posterior of whether it is a cat or something else.
Okay, interesting. So I don't want to go deep into this. I think these are great discussions though, but the way these have been modeled is kind of, you see a signal, you may do a Bayesian update, but you did receive a signal. And so you did receive the signal that said cat.
Oh, I see. So the signal contains the right level in it.
No, it may you may get a noisy signal. So
It contains a label.
sorry, say it again.
It contains a label.
It contains a label. It's like, you look at an assignment, and you think about what grade to give the assignment. That's your signal. Now, if the world is not very noisy, then everybody may strongly agree with you. But if the world's noisy, things might be more spread. And the agents may also vary in taste.
Yeah.
Okay.
So just to clarify that, should I think of the strategy space as exactly the signal space, 1 through m?
Exactly, yes. So the strategy space is a mapping from a signal to a distribution on signals. Okay. I've got 15 minutes. Let's see, where am I? Slide 8 or something? I'm going to try to push on a little bit. Solution concepts. So because the payments decompose across shared tasks, we can do all of the analysis in terms of the expected payment on any given shared task. So EFG is the expected payment for strategy profile FNG on a shared task sampled from the distribution. Going to be interested in Bayes-Nash equilibrium. So this is a slide where I'll make things formal, so hopefully this will explain your question, Nicole. So properness means that being truthful is in equilibrium. If you want strict properness, you need a strict inequality there. Here's the strong truthfulness definition. I think you'll agree it is very strong. It says that the expected payment for being truthful is at least as much as any other pair of strategies. And it says if there's a tie, so if this is an equality, then F and G must be a permutation strategy. In fact, they must be the same permutation strategy. So we're not going to have anything to say about that, but I think you'll agree we can dispense with that.
Permutation means permutation of the truth or permutation of the...
Permutation of the signal you've received. So you play a bijection on the signal you've received.
Are those inequalities ever going to be realized as equality? I mean, doesn't that get you into trouble?
Permutations, yes, equality.
Doesn't that get you into trouble with this argument of why should people invest to do the cost? So you needed a strict separation of...
But it's only in regard to permutation, and you can't play a permutation if you don't have the signal.
Okay.
Permutation of the truth.
It's permutation of the costly signal you've acquired. Okay? In particular, an uninformed strategy will be strictly less than being truthful. The only tie I allow is with regard to permutation strategies. And then this other property that we think is interesting is informed truthfulness is slightly weaker. This bit's the same, so this is still weakly true for every F and G. But now, if this is an equality, F and G had better both be informed. Okay, so we still get the strict separation between informed and uninformed. And by the way, strong truthfulness implies strict proper, and informed truthfulness implies proper. Okay. Let me describe a family of mechanisms. And you'll agree they're quite simple conceptually. They'll be parameterized by a score matrix S. Score matrix just a mapping from pairs of signals to a score. And whereas we normally imagine, in the game examples I gave you earlier in my talk, we normally imagine just scoring you on a task, what we're now going to do is we're going to assign agents to the multiple tasks. We're going to get the reports. You can think about that happening simultaneously on all of the tasks I've assigned the agents to. And then for every shared task, I'm going to pay, again, both agents 1 and 2, the score they get for their reports on that shared task minus the score for a random report that I pick from the set I assign to agent 1 and the random report I pick from the set I assign to agent 2. That's the design. So I look at a shared task. I say Costas and Eric both provided a signal, a report on this task. I score you on that. And then I pick something else you said about a different task and something else that Eric said about a different task at random. And then I subtract that score. Okay. So by the way, you can also replace this with the empirical average if you want to. That doesn't change the mathematics. You can take all LM pairs. But I'd like you to imagine the scheme. What is this doing? The intuition, hopefully you have here, is that now this is kind of rewarding the excess agreement you get because of things, let's say, being correlated or as understanding the correlation structure on the same task, and kind of only paying you for that agreement over the agreement you're getting even on things where you're responding to a completely different task. So, for example, the thing we were worried about earlier in the talk is that you might just say 1 all the time. Right? If you just say 1 all the time here, your payment is 0. Okay. This is 1 and 1, and this is 1 and 1. So you see that if you say 1 all the time, this has knocked that out. Ilya?
So what if agent 1 says 1 all the time, agent 2 says 1 on the shared tasks and 0 on the...
We're assuming the agents don't get to identify the shared tasks. And if you're unhappy about that, I could say lots of things, but one thing I'll say is imagine that I actually assign these tasks to every agent. which I wouldn't want to do in a big system, and then I randomize after the fact.
So are you assuming that the tasks are indistinguishable? Like, it seems like this is susceptible to say.
Conditioned on the signal. Conditioned on the signal. There's nothing else you
If
know.
I were to report like the first bit of the description of the task or something, like if there's something in the task that we can coordinate on.
You only have the signal space, so kind of you don't have an arbitrarily rich signal space you can report. The technical assumption that we need, and I believe this is all we need, is that you don't know anything beyond the signal. So you may be imagining something that's outside the model. Let's take that offline, but I'd be happy to talk about it, but I think I've only got 10 minutes. So. Okay. So hopefully you have a little bit of intuition. I should say this basic idea is in the desk group to Gauche paper. Okay. And as I say here, if in particular the score matrix is the identity matrix, so it only pays for agreement, then, meaning it looks like an output agreement matrix, then this is exactly the multi-signal generalization of desk group to Gauche. Okay. I think I want to just try to convey some basic intuition for the way we do our analysis. And this delta matrix we found really crucial. So let me explain this delta matrix. So let's write down an expression for the expected payment given strategy pair F and G. This is just algebra, all this is. Nothing complicated here. But it turns out this delta is going to be very instructive. So what's the expected payment for a pair of strategies F and G? Well, this is going to represent the expected payment on the shared task. And this is going to represent the expected payment for kind of the L and the M that I sampled at random from the other tasks. And so on the shared task, I'm going to consider all possible IJ signal pairs. These are the signals the agents get. I've got this joint distribution here. And then for any given IJ signal pair, remember we get paid $1 if the score matrix is the identity matrix if we report the same signal. So I'm going to sum out over all possible reports the probability that the joint probability that we both report that same signal. Okay, so this is the amount I get paid on shared tasks. And then the amount I get paid in that second part of the payment term has a very similar form. The only difference is because these are now disjoint tasks, I just use the marginal probabilities here. Okay. And so if you write that down, you get this expression. So you get this expression that says the expected payment for a strategy pair FG is the sum over IJ of this delta IJ matrix, and then multiplied out with the product, with the sum product of these strategies. What is this delta IJ? It's this. It's the, let me draw this. It's the joint probability minus the product of the marginal probabilities. So this is the delta matrix. What's going to be really important to get the results on the paper is actually the sign structure of this. Okay. And what is delta IJ? It's the joint probability minus the product of the marginal. Another way to write this is Pi multiplied by Pj given I minus Pj. So in other words, delta Ij is positive if the conditional probability of the other agent getting J, conditional on you getting I, is larger than the marginal probability of J. So in other words, delta Ij is positive when there's positive correlation. When you receiving this signal increases the conditional probability of the other agent receiving that signal 1 is larger than the marginal probability. And so you might think that the world matrices might look like this. This is what we actually call in the paper a categorical domain. So this is a domain where we have correlation, we have positive correlation on the leading diagonal, and then we have negative correlation everywhere else. So if I think the grade is 1, then the conditional probability that the other agent will think the grade is 1 is higher than the marginal probability. And the conditional probability the other agent will think the grade is 2 is lower than the marginal probability, the same for 3. So think about a categorical domain that would tend to have this type of structure. For example, an image labeling domain where I show you a picture and I ask you, how does this creature move around the world? Does it fly, does it swim, or does it walk? There you might expect this type of domain, because you might think that the disagreements are kind of happening in an unstructured way relative to what you think the signal is. Whereas in a grading setting, let's say the grade is on a scale from 1 to 100. If I think the correct number is 75, that might increase the probability that Costas thinks the correct number is 75, but it might also increase the probability he thinks the correct number is 76 or 77 or 78. So you think about that more as an ordinal domain, where there's some metric space that the signals are embedded in. And so this is a categorical domain. We want to get positive results in more general domains than that. And if you're wondering, the expression for expected payment generalizes in a clean way to settings where the score matrix is non-zero 1. Okay, so in the interest of time, I think I'm going to tell you the main results, give you just a quick look at the empirical results, and then I'll wrap up. I've got about 5 minutes. We can show that it's sufficient to focus on deterministic strategies. I'm going to skip the technical reason why. Which ends up actually being very useful to simplifying our analysis. Let me tell you our results. So the first result is that the OA mechanism, which is the direct generalization of the Descriptor-Gauche mechanism, is strict, proper, and strongly truthful if the world is categorical. And we show that this is tight as well. And we obtain their results as a corollary of that result. I'm going to skip the analysis, but it's very straightforward. It all fits on a slide. So you might say, okay, are we done? So I say, I know how to design a multi-signal scheme with the properties I care about. As long as the world is categorical, are worlds categorical? So we went into our data from these exercises across a number of different MOOCs. And first of all, we asked, for the questions here, so for example, the questions might be like this. This is one where there are 3 possible signals, and you're asked to score the student on not much of a style at all, communicative style, or strong flowing writing style, corresponding to signals 1, 2, or 3. So this would be a world where there are 3 possible signals, and we're ordering the results that I'm showing you here by the number of signals in the world. And first of all, we have strong, a lot of the worlds have positive correlation, meaning that we have positives on the leading diagonal. However, the majority of the worlds are non-categorical, meaning we also have positives off the leading diagonal, which means that we're not done, means that the output agreement mechanism generalizing Descriptor-Gauche is not enough. So the second mechanism we have modifies the scoring matrix like this. So it says, if this is the structure of delta, this is the score matrix you should use. So it's got 1s where there are pluses and 0s where there are negatives. Here's a theorem. For general domains, this 0-1 mechanism is informed, truthful, and proper. I'm going to skip the proof argument, but again, it fits here. So this delta analysis is really helping to prove these results. And then the final mechanism, so what's unsatisfactory about this? Well, you might tell me that informed truthfulness is not enough. And I think in particular, if I drop outside of a binary effort model, I would agree with you. So let's see what else we can do. The ABCD mechanism, now you see why the A's, the B's, the C's, and the D's, has 4 different numbers in the payoff matrix. And just to give you an example, suppose that the delta matrix looks like, and it works. Suppose the delta matrix looks like this. Then the score defined, the score matrix defined in the ABCD mechanism is going to put, so let's say ABCD are 0, 1, 2, 3. It's going to use the B and the C on the leading diagonal. And it's going to use the C where they're positive, so it's going to do 2, 2, 2 on the leading diagonal. And then off the leading diagonal, it's going to use the 0 and the 3, and it's going to use the 0 for negatives and the 3 for positives. So it's going to have this structure. So this is the score matrix that would correspond to this delta matrix.
How about 1?
I didn't need 1 because there was no negative on the leading diagonal. Okay. So what's the theorem? The ABCD mechanism is strong truthful among symmetric strategies. So now it's a slightly weaker strong truthfulness claim. It's not across all FG pairs, just symmetric FG pairs. And I didn't say proper. So this is a thing that actually is curious. Don't have time to get into the details, but it's not proper. However, any equilibrium in a large economy has strictly less payment than playing truthfully. So this has this prisoner's dilemma flavor to it. So you might think this is actually a good mechanism. We won't know until we try it. Okay, let me just let you look a little bit at, we had 104 different questions. So these are the delta matrices across 104 different questions across the 17 MOOCs. And the reason I'm showing you these are questions where it was true false. So you see they have the positive is red, negative is blue. They have the categorical structure. The 3x3s also generally have the categorical structure. So you see red on the leading diagonal and blues off. But when you go to 4x4s, you see this kind of thicker red bands on the leading diagonal. So non-categorical, meaning the types of things happening that I described earlier. So I have some more things to tell you about that, but I'll skip it. There's a review of our results. Let me spend a minute on discussion, if that's okay, Eric. So here is where I think we stand, and here is some future directions. Is there a proper and strong truthful, perhaps a strong truthful amongst only symmetric strategies mechanism for general domains? This result does not exist in the literature. One thing I wanted to note is that you can generalize the mechanism I described by using a different score matrix for the shared tasks and the non-shared tasks. We don't know yet whether that will help. Can heterogeneity be handled? In a sense, we can already handle heterogeneity because I need to know the plus-minus structure of the delta matrix. But you can imagine that it becomes less and less plausible for me to know that matrix as the world becomes more heterogeneous. So the mental model I like to adopt here is if I can learn something about your taste, then I want to try to align you with the taste of a canonical agent. So I'll take the reports from one agent, the reports from another agent. I'll kind of realign them so that they match better, make the world look more categorical. I think that's an interesting direction to be able to handle heterogeneity in a neater way. Is there a prior free design? For example, could we use observed data to then ex post design the score matrix? Would we get the same technical results? We don't know at this point. What about population learning? We haven't talked about this in this workshop. We've been oftentimes assuming equilibrium. But I think that most of us really believe that equilibria are probably not just played through introspection, unless it's a very high-stakes environment. I think we probably believe that they're important because it's where the world will end up with enough time. Maybe we don't even believe they're important even with that. But so what if we modeled replicated dynamics on these? Would the world go in the right direction? We have some results on that I won't show you in the interest of time. Richer models of effort we talked about. And then I think these things are ready to be tested, experimented with, and applied. So thank you.